Welcome to the Hitchhiker's Guide to Calculus. My name's Kevin, and I'll be your guide to Chapter 1.10, the Squeeze Theorem. Now, this is seldom used, but it is helpful anytime you can't evaluate a limit by any of the other methods that we've discussed so far. And it's easiest, I think, to get a visual first, to see how and why this theorem works. Take a look at this function. We'll call it f of x. And I'm just going to draw this, and imagine it's going to be the bottom of our story. I'm going to draw another function. We'll call it g of x, this green one up here. I'm going to call it kind of the top of our story. All right. And our question that we're going to be asking ourselves is, hey, what's happening to this function in between f of x and g of x? This purple one, I'll call it h of x. If this h of x function is always in between f of x and g of x, then we can apply what we call the squeeze theorem to help us evaluate the limit as x approaches a of h of x. First, notice, as we said before, that h of x is definitely between the g of x and f of x functions. So I'm just going to write that in inequality notation. And you'll notice in the graph, at x equals a, all three of these functions kind of squeeze together at that y value of L. So we're going to use that fact, and in our inequality, we're going to take a limit of all parts of our inequality. So the limit as x approaches a of g of x, the limit as x approaches a of h of x, and the limit as x approaches a of f of x. Now maybe we don't know anything about h of x beside it being between f and g, right? But maybe we know a whole bunch of stuff about f and g, specifically how to evaluate the limit as x approaches a there. We can see the limit as x approaches a of g of x is particularly L. That's exactly where it runs into. We can see the limit as x approaches a of f of x also approaches L. So if our h of x function is stuck in between these two L's, and the limit as x approaches a of h of x is definitely greater than L and also less than L, there's only one thing that it could be. So it gets squeezed into a value of L. And that's the squeeze theorem. Now let's slide over and look at an example of this in practice. Here we have the limit as x approaches infinity of sine of x over x. Now we can't do too much with this limit algebraically. We learned before, factoring might help, conjugates might help, trig identities might help. We don't have a lot of stuff to do. So what we're going to rely on is actually what the sine of x function does and what we know about it. If you remember the sine function, I'll draw it over here real quick. All right, the sine function just fluctuates between -1 and 1. It starts and has its center on at the origin and just goes up to 1, down to -1 forever and for always. So it is definitely maxing out at a value of +1 and has a minimum or a bottom at -1. So no matter what, that sine function always falls between +1 and -1. So keep that in mind. If I take our function, sine of x over x, I know the sine is always less than 1, so I can say our function is less than or equal to 1 over x. And since sine of x is always greater than -1, I can say our function is always greater than or equal to -1 over x. This is important. This creates the squeeze that we're looking for. Now we take the limit of all three parts of our inequality as x approaches infinity. And we don't know what's happening to our middle piece. That's the question. But the nice thing about the squeeze theorem is we do know what's happening on both ends of our inequality. Now, those are limits we've talked about before. And as x grows, we're going to have 1 divided by a really large number, which will take us to 0. On the left side, it'll still take us to 0. And the limit in question, the one that we're worried about, is squeezed between two zeros, meaning there's only one place that it could possibly go, and hence the limit of our function must also be 0. Now, as I mentioned before, the squeeze theorem is not commonly tested on the AP exam, but it does exist, so we should be aware of it and how it works and how it functions. Now, if you found this helpful, make sure to check out our other videos in our Hitchhiker's Guide to Calculus series, especially the next one that's popping up now on the different types of discontinuities. Don't forget to hit subscribe and like the page to get alerts about all the content we release each week.